Okay, ladies and gentlemen, thank you so much for the opportunity, Mr. Chairperson. Thank you for the opportunity to present to you two of our CSIR projects that's running in the field of titanium. This presentation will cover titanium metal production and then a separate program which is focused on additive manufacturing and then specifically also titanium. So you will see two names on this presentation. It's actually a paper that was submitted by myself and my colleague, Dr. Dawie van Vieren, who's sitting there in the back. So this is a joint session. We agreed that I will present both these topics, so I am by no means claiming that I'm an expert in titanium metal production. So please, if you have very difficult questions like some of the previous questions we have seen this morning, you're also welcome to address this to Dawie van Vieren that's sitting there at the back. I can try and answer all the additive manufacturing questions. So these two projects are also spanning across two organizational units within the CSIR. So the titanium metal production process is sitting within the manufacturing science, material science and manufacturing unit, and the additive manufacturing programs is run within the National Laser Center. Okay, so the talk will cover the South African's global titanium position. So just how much do we have locally? You've heard the Deputy Minister speaking about this morning. The beneficiation strategy that was agreed already a number of years ago, and then just highlights of these two programs that's running at CSIR, primary net titanium metal production and then our large area high-speed additive manufacturing program. Now South Africa's titanium position, we've got about 17% of the world's reserved in titanium. It's basically embedded in mineral ores, and the mineral production and slag production is similar to what is produced worldwide. Our biggest challenge is that we don't really have a metals production industry. So if you look at the bottom of that slide, in terms of sponge, ingot production and mill products, at present there's nothing. And if we're really serious about developing a vibrant titanium industry and ensure that we actually beneficiate the local resources that we have, it's important that that part of the value chain is also addressed. This is a market that's growing, so it's not nearly as big as the mineral production and the pigment production, but in terms of value, it's much higher, and I'll show you a slide that specifically addresses that. So the titanium metal production project or strategy is really to say, how do we address this particular aspect which is missing from the beneficiation value chain for titanium. So in 2007, the Titanium Center of Competence was established as an implementation vehicle of this beneficiation strategy. So in this talk Björn just presented, you would have seen one of the mechanisms that is set up to support technology development is centers of competence. So the Titanium Center of Competence was developed, the whole strategy was developed based on some industry interaction. Department of Science and Technology then contracted the CSIR to set up the Titanium Center of Competence. And as you can see from the slide, it's a pretty old and well-known slide already, but it's very impactful because it gives you the full value chain of what is required to get the titanium metal manufacturing or titanium industry up and running. We start with titanium primary metal production, then powder consolidation to produce, for instance, mill product. Another way to produce components is additive manufacturing, investment casting, high performance machining, friction welding, and sheet forming. Now the Titanium Center of Competence is actually a collaboration network of various parties that contributes to technology development specifically. It's a focus on technology development, which is supported by a whole range of competences and design and, competence in design and simulation and modeling, laboratories and R&D facilities across the country. With a main aim to develop technology that can lead to industrialization and commercialization, with the ultimate view to transfer this to suppliers in those industry sectors, and in this way actually stimulate a very vibrant titanium industry. So the two programs that we're talking about today is then specifically this aspect here, the primary metal production one, and then the high-speed additive manufacturing one. So this slide gives you also same kind of picture in terms of what is the value addition when you start with the basic metal bearing ore, which is ilmenite. Typically, what is the cost for this and what is the process to get to a final product at the end of the day. And if you can just see the price increase as it goes up, $1 per kilogram of ilmenite, and then getting, well, anything depending on how complex the part is, anything between $150 per kilogram of part up to $20,000 per kilogram of part. So if there's technologies in place that can actually reduce the cost to develop, to extract and to have the titanium metal ready for part production, obviously one can reduce this whole cost structure, or additionally you can actually create a very vibrant industry with this technology. Presently South Africa's current industry is limited just to these two, the ones at the bottom, the mineral extraction as well as the titanium dioxide slag production, and then some of this taken into titanium dioxide pigment, which is this whitening agent one sees also amongst else, and I think in toothpaste if I'm not mistaken. So the titanium metal production system is really to say to what extent can we change this whole process. This process to produce titanium mold products is based on what is referred to as the Kroll process, which is a very old process. It's a batch process. It works, but there's not been a lot of innovation in this process. And the process that was developed and patented here at CSIR then actually looks at a whole new way of producing titanium powder, which is based on a wet chemistry-based process with significant cost savings at the end of the day in terms of the price that you pay per kilogram of titanium powder. Obviously the titanium powder can be used in additive manufacturing, or it can go into a process to produce titanium mold products, which can be then normally machined and produced. So the titanium pilot plant timeline looks as follows. I think the contract for the phase 2, the pilot plant development, was started roughly about 2011, late 2011. So they are presently in the stage 3 area, which is having a continuous plant producing about 2 kilograms per hour. That is the target. And in this activity, the following tasks are typically seen: concept design, cost estimate and feasibility, basic design, construction, commissioning, and the operation of this plant. Once that is successful and they've proven the concept, it will move into the feasibility study phase for a full demonstration plant with a view to run up to 500 tons per annum of commercially pure titanium. That's an unalloyed titanium metal powder. Timeline for this, plans are to get this to about 2020 and then move to a world-class plant of producing about 20,000 tons per annum. So this is just a very complex flow diagram of how the process works. Main input being titanium tetrachloride. So it's a self-sustaining process. There are obviously lots of energy going in, but this just to give you an indication of what this process works like. So if you have any more questions, you're more than welcome to ask Davi, who will explain this to you in detail. What I can talk about actually is the advantages of this process. So first, well, this kind of approach really allows you to do continuous operation. As I've mentioned, the Kroll process is a batched operate process. One obviously gets economy of scale if you start producing at higher levels. And a very important aspect, this actually allows us to go directly to titanium powders, which are very important for more effective manufacturing technologies such as additive manufacturing, bypassing the sponge and the ingot formation processes, which are also energy intensive. I think there's about 12 other similar programs running in the world to produce titanium in this way, but there's some advantages specifically with the CSIR patented process, in that this process has got one of the lowest processing temperatures, and obviously for corrosion and operational problems in terms of your plant, this is very important. I think a very important point here as well is that in this process, there's also the opportunity to control the powder morphology. So for some manufacturing processes, it's very important to have nice spherical particles, and typically these processes presently provides different kinds of shapes or powders, which makes it difficult to use in manufacturing processes. So this process lends itself also to some control with this regard. This is a picture of the pilot plant as it stands now. So I think there's the main reactor there at the back. If I understand correctly, there's also, you could have registered for a tour to the titanium pilot plant, which happens tomorrow. So you most likely will then see this facility also set up. Okay, then the second part of this talk really talks about additive manufacturing. Bjorn this morning mentioned some of the activities that's happening elsewhere in the country, notably at Vaal University of Technology and the Central University of Technology, where there are technology stations. Björn also mentioned that we have developed an additive manufacturing roadmap. And I think I want to mention at this stage that we have also got an implementation vehicle for that roadmap, which is called the CPAM, or the Collaborative Program in Additive Manufacturing. And I'm not going to present any information on that program during this talk. There's just not enough time to do that. Bearing to say that we have got a national network also that focuses on additive manufacturing technology development, focusing on metal production technologies, polymer production technologies, and then as well as the thinking about design concepts and how one should change the mindset of designers to actually get the full potential of additive manufacturing. To start with additive manufacturing, it's always important to understand what the definition of this is, and this is the accepted definition according to ASTM. As the process of joining materials to make objects using from 3D model data, usually layer upon layer, as opposed to subtractive manufacturing. So I always think about additive manufacturing as having to make a component from metal you mill away, or a statue you chop away from the granite block to leave the statue, subtractive. Whereas additive manufacturing, a good example of this is as a house that you build. You start with nothing, but you put bricks where you want walls, and this is exactly the way that additive manufacturing works. So in industry, we start with a CAD model. We change this to a STL file on your computer. You slice this, still on your computer. That sliced information is then fed into your printing machine or your additive manufacturing system, and then the machine then basically prints your final part. There might be some finishing required, but you can see that there's little tooling involved. There's no all different in complicated manufacturing processes. If you see the part in CAD, you can actually generate this with a printer directly. It's a significantly growing industry. So it was invented in 1986 or 87. It's not that long ago. I was already working at the CSIR when it was invented. So this shows you how recent this is, if you look at my age. But it's growing significantly. It's now currently about, I think, a $3 billion industry worldwide, and it's growing annually at about 16%, and has been growing like this for the last 10 or 15 years. I think more importantly for us is that if you look at this graph, which basically states what is the adoption for additive manufacturing for final part production, this has been growing significantly. Additive manufacturing has always been seen as something that you can just use to print prototypes, nice something that you can put on the corner of your desk. But as you can see from 2003, where only 4% of all additive manufacturing activity was focused on final production, we're sitting at the end of 2013 at 34.7%. So additive manufacturing is moving into the realm of actually making final part production. And that's a very important point, but it's also very important to understand that there's lots of research and development work required to ensure that the standards and the qualification processes are in place that we can produce reliably with this technology. This is for sure something where we are not at yet. This talk is a little bit focused on titanium, and for that reason we need to think about aerospace. So where is additive manufacturing used in the aerospace sector? The main advantages of additive manufacturing is that you can actually use material very sparingly. You can use materials which are typically conventionally very difficult to manufacture and to machine. And you can actually reduce component count by having new designs which are much more efficient, but couldn't be manufactured with conventional manufacturing technologies, and which additive manufacturing now actually unlocked for you. So these bullets here give you some of the examples of where the advantages of additive manufacturing lay. Some pictures here on the right. So very complex parts, which is not possible with conventional manufacturing technologies. And even direct production of tooling, if you have limited production runs. You now get to the point where there's some good materials available where you can actually print your tool, and with a limited production run, we're able to produce stamped parts or formed parts without too many problems. Our focus is largely on titanium, as I've already said, so this is a big focus on the aerospace industry, and I think the main motivation for this lies in the next couple of slides. So you will see that there's a big drive internationally to reduce the weight of aircraft. Why? Because we want to ensure that our airlines or our aircraft is running more effectively or more cost effectively. So there's two ways of doing that. Firstly is to ensure that you operate your aircraft at the right speed that it's designed for. The second big thing you can do is to reduce the weight. There's some numbers published which says that for every 1% reduction in weight, you will reduce your fuel bill by about 0.75%. So there's a very big impact in terms of reducing weight with respect to the cost of operating the airplane. And if you think about the lifetime of some of these planes, the cost savings can be significant over the lifetime of the plane. So the way to do this is to go to composites. The big challenge with this, however, is that traditionally we used aluminium for our airframes. But due to the fact that you get galvanic corrosion between composite materials, typical composite materials, and aluminium, you need to think about a new material. And titanium, being a very light alloy, but also a very strong alloy, is the ideal candidate for this. However, there's some challenges with titanium with respect to cost, as well as to machinability. Very difficult to machine alloy, which makes it the ideal candidate for additive manufacturing. So the next couple of images just show you some percentages of what's currently happening in commercial aerospace. The Boeing Dreamliner, 50% is now composites. This is a graph that just shows you the progress within Airbus. The A350, which is now just being released and starting to fly around, is now more than 50% composites. And this is just a breakdown in terms of the material composition. So 52% on the A350, with already sitting at 14% titanium. So this is a real important point to remember once we start thinking about why we use titanium. I've touched on the basics of this slide already, but it just gives you a little bit of a pictorial view. So if you want to produce components in titanium, you have to go through this process of mining the ore, go sponge, ingot, and billet. This is the Kroll process. And then extensive machining if you have very complex aerospace parts where you reject about 90% of, well, throw away 90% of the material as waste, ends up as shafts in a waste bin. If one compares this to the additive manufacturing process, where Davies process now can allow us to go from ore directly to powder. So we have a very strong South African capability. I'll talk about that now. And there's also some capabilities in South Africa regarding machining. So it makes sense to think about what additive manufacturing technologies can be developed to ensure that we beneficiate our powder. The two little ships that came in was, I forgot to mention that, but for the South African manufacturing industry specifically, the additional challenge is because we don't have this metal production industry. As I've mentioned on the first slide, we're exporting all the ore, and then we have to re-import billet, which is obviously just another cost driver in the process. So in additive manufacturing, although the technology is growing, there is at present some severe limitations, and this is one of the things that we've been addressing with this particular project, high-speed, large-area additive manufacturing. So currently, commercial systems are suffering from inefficient laser manipulation. The laser beam is basically scanned across the surface, and there's not really a way that in present systems allow you to speed this process up. Laser sources is basically a welding process. So the amount of laser power that you have available is currently limiting you in terms of the energy input. And then the way that the whole system is designed in terms of the putting down powder, doing the scanning, moving the bed, all this is a serial process. So we thought about ways that we can actually speed up this process as potential to address these limitations. A very important point is that currently commercial systems are limited in terms of part size. So if you start thinking about very large aerospace components, you cannot really do this with additive manufacturing as yet. Just to give you an example, this is a part which I think is from Boeing in titanium, which is machined from billet. Currently, commercial systems in additive manufacturing does 300 or 350 by 350 by 350 millimeters. So that a component like this is not possible. Now you can just imagine what big block of material you would have required to actually machine that component out. And this is typically a very good candidate for additive manufacturing. Similar to this component we see here at the bottom, which is actually the wingtip of a A400M. The weight of this part is about 4.2 kilos. The bulk material, and this is actually aluminium, not titanium, is 270 kilos. So you actually mill away most of that block to produce that part. And this is a very good candidate again for additive manufacturing. Presently, additive manufacturing is also subject to high costs, and that's mainly due to the fact that we have limited throughput. So the process is slow, limited in part size. So if you can address a new technology that will actually address those challenges, one can really make this process affordable. And then, as I said, also when I showed you the growth in the application, or in terms of using additive manufacturing for final part production, the qualification process is still lacking. We can print, but can we reliably print for manufacturing industry? So those are the limitations. So this project that we then started embarking on in 2008 already has the objective to develop a large area powder bed AM system for metallic components. Large area because we want to ensure that we address the aerospace industry. Powder bed because we want to ensure that we can actually print components with high resolution, so very complex components that cannot be manufactured or machined in conventional manufacturing processes. And then high throughput with the idea that we can actually do batch manufacturing as well. So we can decide whether we want to have just one large component in the system, or we want to have a whole bed of little small components and printing them at the same time. So the system as it's designed has a build size of about 2 meters by 0.6 by 0.6. We have also made this scalable so that we can decide to have smaller bed sizes if required. And the machine is designed to allow us to process Ti-64 or titanium 6 aluminium 4 vanadium, which is the alloy of choice not only for aerospace but also for medical applications, stainless steel alloys, inconels, as well as other metals. Maybe just to touch quickly on the two technologies which is important when you think about 3D printing or additive manufacturing in the metals environment or metals industry. This is the Aeroswift process, which is called the powder bed fusion process. So in this case, you have a thin layer of powder which is then consolidated or welded where the laser beam basically touches the powder, so the laser scans across the powder bed surface. After you've consolidated the first layer of your component, the bed drops and you deposit a new layer of powder and you do the second slice of your component. So this is powder bed fusion compared to what we call laser metals deposition or direct energy deposition, which is the correct ASTM term, where we actually blow metal powder into a laser beam, and wherever you move the laser beam and the laser powder nozzle, you deposit a weld bead, and in this way you actually can also build up or print a component. The comparison of these two is listed in the table here. I think importantly there's some advantages in this technology, and there's also advantages in this technology. So in this case we can do what we call functionally graded builds, which means that during the build we can actually change the alloy composition to allow us to get different properties at different levels of the component. As I've mentioned, we've got size limitations in this technology. However, Aeroswift is actually addressing this by increasing this with a significant increase. We can do very complex parts where this is limited. And if you look at consolidation rates, commercial systems typically do about 20 cubic millimeters per second, where we can now with Aeroswift demonstrate it up to 60 cubic millimeters per second of titanium 6-4 powder. And then geometries and surface roughness effects. So this is a very simple graph, but it just demonstrates where Aeroswift fits into this competitive landscape. So if one have this, the capabilities plotted in terms of part size on this axis versus the complexity of the part on that axis. So present commercial powder bed systems basically are small parts but very highly complex parts. And if we think about laser metals deposition, the one that I've just showed you, we have larger parts possible but less complex parts because we basically spray the powder into the laser beam and the robotic system depends the resolution. And then one can go to very, very large systems where you actually move away from laser-based processes, but actually use a welding process, combining it with wire and depositing large structures with a welding process. Aeroswift falls in this domain where we have already significant larger part size, but also then the potential with high complex components, and obviously you want to sit in that top right-hand quadrant to get high value components. So the project started in 2011 formally. So during 2008 and 2010 we did a proof of concept study and demonstrated that the principle, the way that we developed the technology will work. In 2011 we started with the design and the construction of this machine. This is the Aerospace machine. Phase 1 was basically the design and construction, and that's now completed. It was finished about November 2014. In the beginning of this year we started with the next phase of this work, which is developing the process parameter window for this machine, looking at the material produced with the machine in terms of mechanical properties and repeatability to ensure that we have the possibility to have a qualified process with the ultimate aim, to have a flight ready part at the end of 2017. That means we need to have an aircraft designed part, and we need to have been able to print this and to take it through all the testing which is required from a commercial aerospace environment to have this ready. And I think if we achieve that milestone, this technology would really put South Africa at the lead in terms of 3D printing technology, specifically in metals. With respect to technical progress, I can maybe just share this, which is the last slide. This gives you just a summary of some of the technical results that we have achieved with the system already. So this here in the corner is some of the test samples that have been printed in titanium 64. That table there at the right gives you some of the information. So we compared the samples produced with this high-speed additive manufacturing technology with conventional milled and annealed reference sample, and then a sample produced by a smaller commercial machine. You can see here that the impact toughness is very good. It's actually better than the milled and annealed sample. And we have also seen some very promising results with respect to hardness values. Now that's important if you want to think about ductility of the material, and specifically for components that would be high weight carrying and where you actually need very good fatigue properties. So in terms of the metallurgy, this process seems very promising. We are now in the phase to actually develop this and to ensure that we can upscale this and get the first parts produced. Thank you.